any homework questions? Questions on the homework? Pretty easy. I noticed everyone who's turned it in so far, except for one, turned it in online. That's great. I'm sure the grader appreciates that. Yes?
Did you go to 67B?
I will need some assistance since I do not have a book with me.
Oh, it's a long problem. Where did you come up with? Okay.
Get some experience in public speaking right out of the first
Okay.
Can I come up? Yeah.
Okay.
You don't have to ask. You have free reign. You're doing that good. Yes, sir. Sorry. Okay, thank you. But before you go, is this a 5 or a 6? Is this a 5? That's also 5. And that's a 3. Okay, thank you. Yeah. Okay, so define the expression, but they want you to use the law. Show that you know how to use the laws of exponents to simplify this. So the first law that comes to mind kind of goes like this. You know, AB to the n is A to the n, B to the n. And you know, this works even if you have more than A and B here, right? You're going to distribute the n over the items here. So the first piece over here, we're going to have 32 to the 2/5, x to the 5th to the 2/5, and y to the -3/2 to the 2/5. That's the numerator. The denominator, I didn't ask, that's a 5 yet. We have x to the 5/3. Now we're distributing 3/5 over it. And y to the 2/3, 3/5. Okay, so the next law we need to look at is one that says a to the n to the m is a to the n m. That is, when you're raising something to a power, you get to just multiply those exponents. Again, being careful, if a happens to be negative and one of these happens to be even, we have, I think we mentioned a problem. The book said just don't do it. But all right, so what do we got here? Well, I know there's a lot of CS majors in this class. And if are a CS major or not, and you don't already, you should recognize 32 as 2 to some number. Now, you can just figure it out. 2, 4, 8, 16, 32 is the fifth. Okay. So, the fifth root of 32 is 2. They kind of set the problem up that way. And then we have to square it, so it's going to be 4. I hope this doesn't make things difficult. So this becomes 4. X to the fifth, to the 2/5, well, we multiply these two and we just get x squared. Y to the negative 3/2 times 2/5, well, you know, 2's cancel. Y to the negative 3/5. And now we have to deal with the denominator. You can see already x, this becomes x to the 1. And here, these are going to cancel x, y to the 2/5. Now, I don't know if the book specified, you know, no division or what. I mean, you can see here, let me do a little more formally. A to the n over a to the m is a to the n minus m, which we have here, x squared and x to the 1, so 2 minus 1 is x. This becomes 4x. I don't know if the book said anything about no negative exponents or no divide. It doesn't matter to me. We have to move one of these up, combine them. So let me move everything up. 3/5 minus negative 3/5 minus 2/5. We'll write that down. Negative 3/5, 2/5. So we're just going to end up 4xy minus 5. Oh, it's minus 1. So I can either write it as minus 1 or 1. This actually looks nicer, but it doesn't matter. Okay, it's just a lot of work. You know, a little muscle memory for dealing with exponents. And any questions about this? Okay, you know, once you work with these for a while, the main job is no longer figuring out how to do it, it's making sure you don't make a kind of dumb mistake. Negative 3/5 minus 2/5, negative 1/5. No, you just have to do your stuff carefully. All right, any other homework questions or math questions or life, the universe, and everything kind of questions? All right. So we're going to start off today talking about something called a rational expression. We have p of x and q of x polynomials, and p of x over q of x is a rational expression. So, for example, there's a polynomial, another polynomial, that's a rational expression. Another rational expression. Cubed minus 5x plus 6. Another another rational expression, polynomials. Counterexample. This has a radical in it. Or rather, the variable is inside a radical. It's another rational expression. Perfectly good rational expression. Okay. So if I have some polynomial and I want to think about what values x can take, it turns out that polynomials can always take any real number. It's the fact of polynomials. The numbers we decide to put into an expression has a name, it's called the domain. It's very common to see an expression like this, but nobody says anything about the domain. In which case, as a convention, we just assume it's the maximal interval or the maximal number of values that you can put into this expression, which in the case of a polynomial is always all the real numbers. It's perfectly acceptable to say I have an expression and I just want to look at it on this domain, 0 to 1, or any other domain. We sometimes give that a name, truncating. It's a different word. I can't think of the word. I'll look it up. We can call it truncating or limiting, or with rational expressions, that's not the case. That you always can put any real number in. It depends. For this expression here, y minus 2 over y squared plus 4, the denominator is always defined. Doesn't matter whether y is 0, positive, or negative. This is always valid. It's never 0, is what I'm trying to say. Typically the values in a rational expression that we can't use are 0. 0 in the denominator. So this could have a domain of all real numbers. This expression, 2x over x minus 1, has a limitation. You can see right away, x can't be 1. It's got to be undefined. So you can write this as negative infinity to 1 union. What I want to do? Yeah. 1 to infinity. Notice I've used open brackets, so I'm not including 1. And that could be the domain of this expression. It could be smaller, it could be something truncated. All right, now for something like this, x cubed minus x over x squared minus 5x plus 6. Wait a minute. We're not sure right away, right? Could this be 0? Well, the only way to know would be to factor it. That's probably not the only way to know. The way we have to know. Factor it. So I'm going to do reverse FOIL here. X. 2, 3 minus. So minus 2 times minus 3 is 6. Inner and outer, minus 2 and minus 3 is minus 5. Okay. So we have this expression x cubed minus x. And the values, the way I would ask the value, the way the book's going to ask the question is, what's the domain of this? Which is too bad. It's not really a proper question. There's no way to know what the domain is. It could be anything. Well, almost anything. The way to ask the question is, what values cannot be in the domain of this expression? And the answer is 2 and 3. So if we want the maximum domain, we would say, x such that x and m are reals, but x is not equal to 2, and x is not equal to 3. You don't have to write that whole thing. You can just kind of leave this off. That would be fine. You might t equals that's a domain. There's something important about the domain of an expression, which is it's kind of permanent as far as what's excluded from it. So, for example, I might say something like this. I might say, simplify this. Okay. This is, we can cancel the x minus 2. This is x minus 3. That's fine. That's going to work. But what you have to be careful of is if you need to use this somewhere else, you still can't use 2. Right? Because what you're saying, would be saying is 0 over 0 is 1. It's not. So that's something to be aware of about the domain when you're working with expressions. There are these trick problems you'll run into where you simplify and you get an answer, and then you plug the answer back in and it doesn't work. We'll probably see an example before today's over. Well, we're going to see one right now. Okay. So let's say I have x squared minus 1 over x squared plus x minus 2. Now, just a little mini quiz you can do in your own head. You don't have to raise your hand or say anything out loud. What are the factors here? You should look at this and it should take you under 10 seconds to think, aha, I know what the factors are. We'll come back to that in a second. Again, reverse FOIL. Okay, we have a minus and a plus because 2 has a minus in front of it. The only possible factors are 2 and 1. 2 goes here, and 1 goes here. We have minus 1 plus 2, we got our x. So that's good. All right. So want to tell me what the factors of x squared minus 1 are?
The x minus 1, x plus 1.
All right. Everybody should immediately start to recognize a squared minus b squared, a plus b, a minus b. so we can simplify this, rational expression by seeing that x minus 1 over x minus 1 is always 1, unless x is 1. So we can rewrite this as x plus 1 over x plus 2, x not equal to 1. That's important. Sometimes when we're solving something, we'll do something like this, and we'll come up with a solution, 1, and then you plug it back in, and it doesn't work. And I like to call those, if you're solving an equation, you're looking for roots, I call them phantom roots. There are other ways we get phantom roots. Okay. Rational expressions are a lot like rational numbers or fractions. So the rules you know about dealing with fractions are going to come in handy. For example, if you want to multiply AB over CD, that's going to be AC over BD, whether these are just numbers or polynomials. So, for example, x squared plus 2x minus 3, it's kind of ugly, it's all right, x squared plus 8x plus 16, and we want to multiply it by 3x plus 12 over, parentheses here, over x minus 1. Now, kind of a knee-jerk thing you might do, especially if these were just numbers, would just be multiply the numerators and multiply the denominators. But as you might do with numbers, you might want to see if there's some way to reduce this beforehand. And multiply 15 over 4 by 2 over 3. I might want to factor these, right? 4 is 2 plus 2, so this is 2. 15 is 3 times 5, so this becomes 5. It makes it much simpler. The same is even more true of polynomials or rational expressions that we're multiplying. So let's first try and factor these a bit. I'm going to work on this one. I'm going to ask you to think about this one while I'm working on this one. Do things at once. You have two sides of your brain. You can do that. Up here we have x. Again, for a lot of these problems, reverse FOIL is going to work fine, just because they set them up that way. We have minus 3, so we have a minus and a plus. And we have 3 and 1, the factors. Clearly, we make 3 the positive, minus 1 the negative, and we'll get 2x. Okay, that's good. And now we can factor this too. We can take out a factor of 3. That becomes x plus 4. All right, who's figured this out already?
It would be x plus 4 and then,
Yeah, x plus 4 squared. We'll just write them both out. Now, perfect example of that pattern again. A squared plus 2ab plus b squared. This is a square, this is a square. This is x and 4. X times 4 times 2 is 8x. So we know it's a perfect square. And we have x minus 1. Oh, okay, so now we can cancel the x plus 4, one of them. cancel the x minus 1. And we end up with 3 times x plus 3 over x plus 4. Remembering that x cannot be minus 4, and x cannot be 1. I mean, you wouldn't try and plug in minus 4 here anyway. But you might try and plug in 1, right? You get 12 over 5. But if you plug that into the original expressions, you'd end up with an undefined answer. Now, since multiplying rational expressions is pretty straightforward, dividing them turns out to be pretty much the same. Because we know that A over B divided by C over D is just A over B times the reciprocal, B over C. This is BB over BC. So as an example, we have x minus 4, x squared minus 4 divided by x squared minus 3x 4 squared plus 5x plus 6. Well, you can just rewrite that as a product. Instead of trying to divide, we can multiply. So that's just going to become x minus 4 over x squared minus 4 x squared plus 5x plus 6 over x squared minus 3x minus 4. Okay, again, we're going to want to factor first, see if there's any simplification. X minus 4. What we got here? X. I think we've seen this one before. Plus 2 and plus 3. Plus 2 and 3 add up to 5. Down below, we've seen this before, something like it. X minus 2 is x plus 2. And a squared minus b squared. And here we have what? A little work. X. Okay, this could be 2 and 2 or 4 and 1. You can kind of guess already. 2 and 2 you can't combine them, and 3, 4 and 1 you can. This is minus, so one of them's minus and one of them's plus. So we just have to make this work out. Make the minus, put the minus next to the 4 and the plus next to the 1. It's going to work. So we have just a little bit of simplification. And multiply this back together if you want, or leave it this way. You just again have to remember that along with 2, 4, and minus 1, you can't have minus 2 as in the domain of this expression.
And you also cancel x minus 6.
I missed something else? Oh! Snow blind up here. Yeah, thank you. Oh, well, that's much nicer. Minus 2, x plus 1. Thank you. Okay. It's funny how usually you think of addition as easier than multiplication, but when it comes to fractions, you have that added step. C over D, well, you need a common denominator, right? Now, sometimes you can get away with something simpler than this, but you can always just say, right, this is AB times D over D. That's 1, we're multiplying it by. And C over D times B over B, again 1. So we get AD over BD plus CB over EB. And now they have a common denominator, so it's just AB, AD plus CB over DB, or BD. Well, you can do the same thing with rational expressions. So, as an example, let's say 3 over x minus 1 plus x over x plus 2. Well, it's obvious there's no simpler common denominator than x minus 1 minus x plus 2. So we're going to have to multiply this by x plus 2 over x plus 2. So that's going to be 3 times x plus 2. And here, we're going to have to multiply this by x minus 1 over x minus 1. So that'll be x times x minus 1. Might be able to simplify this, though. We have to check and see. X plus 6 plus x squared minus x. I'm going to rewrite that again. So we have x squared minus 2x plus 6. Well, this is supposed to come out that way. Yeah, I'm wrong. X minus 1 times x plus 2. I was thinking maybe they kind of jimmy-rigged this problem so that you could factor this. 6 and 1 cannot make 2, 2 and 3 you can't make 2. So that's it. That's all we can do with it. I guess multiply this out. Same thing for subtraction, right? Put it over a common denominator. And then you just do your subtraction carefully. There's some other tricks. I don't mean that as a magic trick, as in things you might run into. You might run into an expression like this. You want to simplify this. Kind of a fraction over a fraction. Except we have this problem here. So what we want to do is we want to do this sum first, put it over a common denominator, do the same on the bottom. Here we have x minus y over x. But of course, here we have a division, right? dividing two fractions by each other. And of course, dividing fractions, you just multiply by the reciprocal. And here we again, we have a nice simplification. Again, the restriction on the domain of this is going to be as long as x plus y is 0. Write that this way, x not minus y. All right, any questions up till now? This is dealing, I hope this is pretty straightforward and you all feel pretty comfortable with this. There's one more bite to this section, and I know I'm repeating myself when I say this is a really important pattern. It's not just for factoring. We're going to use it when we get to complex numbers. And here, we're going to look at how we want to, well, how we want to simplify it. I don't really, this is the problem book, Dave. I'm going to make it, without doing anything, I'm going to make it more interesting. What we want to do is we want to rationalize the denominator again. How do we do that? We want to get this radical x out of the denominator. No. I'd rather just sit and watch someone else teach the class. No, I'm kidding. Yeah, absolutely. Why are we going to do that? Because we know we're going to end up with this squared and this squared. That's going to get rid of the radical in the denominator. Of course, you can't just put anything up here. You have to put 1 minus x. So in the denominator, we get 1 minus x. In the numerator, we get 1 minus square root of x. Now, with an expression like this, you have to be even more careful. This is not a rational expression. It's a fraction with sum, putting the radical in the denominator. We have to be even more careful about the domain of this, right? There's no problem here as far as x, as long as you can only put in positive numbers or numbers greater than 0 or greater. We can't put in a negative number here because we're just dealing with real numbers. So, for x greater than or equal to 0. This is a tool that will probably come up frequently later in the class. Just a way of simplifying something, getting the radical out of the denominator. Right. So that is it for the chapter on rational expressions. Be some homework, some practice. is a short section. The next section, 1-5, we've already done quite a bit of this. There'll be a little repeat. This has to do with solving equations. So, an equation that we're going to think about solving is going to be some expression. I'll just make something up. It's just going to be an equality with some variable x. And our task here is to find a value of x that makes this equation true. And the methods we use, well, there's just one x in the expression. You want to manipulate it so that you just end up x equals something. You want to use some rules that we're going to talk about. If you have something ugly like this, your task is to combine these x's in some manner so that you can then solve for x. So we're going to start really simple. I hope I'm not insulting anybody here when I write this. This is something probably had, some of you may have had in 8th grade. Certainly in high school. This is called a linear equation. It's called linear because the polynomials involved have a degree no greater than 1. And how do we go about solving this? Well, we have some rules. One rule says that A is equal to B, and A minus C is equal to, well, B plus C, where C could be a negative number. So the first manipulation here is we're going to add -7 to both sides. That's to get x isolated. Right? This is a perfect example of using the inverse property of addition. Right? Every number has an inverse, and the sum of the inverse of a number is 0. So we end up with 4x equals 12. And then we also know that A is equal to B, and A over C is equal to B over C, provided C is not 0. So here we're going to use the inverse property of multiplication. We're going to multiply both sides by 1/4. The inverse of 4, or divide by 4, so we get x equals 3. So that's as simple as it gets. I'm sure you all been through it, know how to do this. Okay. This is a linear equation. Next, we're going to just briefly talk about quadratics, because quadratic equations, we've already talked a lot about them. Quadratic equation being x squared plus bx plus c equals 0, or something that you can turn into that form by manipulating it. You might have to combine terms or multiply. We already talked about the ways to do this. I'm not going to go over all these. Factoring, reverse FOIL, completing the square in order to find the roots. You can factor, quadratic formula. I'm just going to write that down so any of you who are still having trouble with it, you can get it down and you can go down to the local tattoo shop and I will write it down. So this is another set of equations. We've talked enough about how you would solve those. So we're going to spend a little time talking about equations with radicals. An example. Now, the strategy for isolating the variable inside of a radical is, of course, in this case, to square both sides of the equation. And you get x equals 9. Now, this is a very simple example. But what you want to do with a problem like this when you're done and you have some solution is to plug it back in. Now, that may not seem obvious why. Maybe in this case it doesn't seem necessary at all. But what if I were to write this? Well, if you followed the same process, I'm sure you wouldn't. You would get x equals 9 again. But of course, the positive square root of 9 is not -3. So again, this is an example of what I call a phantom root. You solve the equation, you get a solution, but it doesn't work. So you want to go back, check it into the original equation. Now this is way too easy an example that you would ever be fooled by, but let's at least look at something a little more complicated. So let's say we have 2x equals 1 minus square root of 2 minus x. There's really two ways to go about this. I encourage you to isolate the radical first. But if you think ahead, you could use that a squared minus b squared pattern. Multiply this by 1 plus square root of 2 minus x. That will work. But let's kind of back up here. Subtract 1 from both sides. square both sides. Oh, minus times and minus is a plus, so we just end up with minus x. Let's multiply this out. And again, let's combine terms here. 4x squared minus 3x minus 1 equals 0. How am I going to solve that? Well, I think my temptation is just to use the quadratic formula, but I'm going to try and FOIL it anyway. I know that I either have 4x times x, so I have 2x, 2x, and I have to end up with minus 1. So one of these will be minus and one will be plus. Here I can just put them in, so it's not going to matter. Okay, so if I put one of the factors, there can only be 1. So, oh, well, that was more than equal nothing. So now the question is, where's the plus and where's the minus go? Looks like the minus goes here and the plus goes here. Okay. So I have 4x plus 1 times x minus 1 equals 0. And that, of course, tells me my roots are 1 and negative 1/4. Or are they? Let's take a look. So if I plug in 1, I get 2 equals 1 minus square root of 1. Oh. Did I do that right? Yeah, I did. 2 does not equal 0, does it? Right? This is a phantom root. It's not a solution. So you need to go back and check. I guess we should check minus 1/4. So 2 times minus 1/4 is minus 1/2. Equals 1 minus square root of 2 minus a fourth. That's plus a fourth. Square root of 9/4. 1 minus 3/2, which is minus a half. Okay. That is the root. So again, when you're dealing with radical expressions and you're solving equations with them, you have to be a little careful. It's okay. I say it's okay. We're still talking. We're a little ahead today. Okay. So we're going to go a little further with solving equations. We're going to look at some ideas on how some problems which might seem a little more difficult, maybe aren't. So here we have a 4th degree polynomial, a quartic. And in general, it could be pretty difficult to find a solution. But sometimes they're not. You have to look at this. This looks kind of familiar. Right? Yeah, it looks kind of familiar. It looks a little bit like a quadratic. It only has 3 monomials. It's a trinomial. But it's not quite clear how are we going to go about this. Well, the trick to see is that we have x to the 4th and x squared. X to the 4th is just x squared squared. It's kind of like what you see in a quadratic, except you see x and x squared. So the trick here is to change the variable that you're solving for. What we want to do is we want to solve for another variable, y, which we're going to call x squared. When we substitute this in, we're going to get y squared minus 8y plus 8 equals 0. Now we have a chance to solve this using the techniques we've already developed. This is not going to factor, so let's use the quadratic formula. That would be y equals negative b, which is 8 plus or minus the square root of b squared, or minus 4ac is 32 all over 2. Or 8 plus or minus the square root of 32, 2, or 8 plus or minus, well, here I'm going to reduce this, radical. This is 16 times 2, square root of 16 times the square root of 2, or just 4 times the square root of 2. So 4 times the square root of 2 over 2, or it's 2 plus or minus 2 square root of 4 plus or minus 2 square root of 2. You write those out. 8 plus 2 times the square root of 2, 8 minus 2 times the square root of 2. That's y. Right? We're not looking for y, we're looking for x. That's okay, because we can plug each one of those solutions in here and say x squared equals, what did I do here? What do you even say? My right hand doesn't know what I'm saying. 4 plus 2 squared root of 2. Okay, so x is plus or minus the square root of 4 plus 2 square root of 2. Now that's not very pretty, but it's a number. Solution. We also can substitute the other root. And you may have observed this. There are 4 roots. We have a 4th degree equation, and we're going to find that when you have a polynomial equation of degree n, it will always have n roots. Now they may be duplicate roots. How about this? This has 5 roots. They're all 0. It doesn't have distinct roots. Okay. So that's a trick you should know about. It will sometimes come up differently. You might see 6 minus x cubed plus 8 equals well, same trick, except I say y equals x cubed. The thing to look for is if the exponents have a common factor, you can do this. You can simplify, the solution. Now, having observed that trick, you might want to see if you can apply it again to an equation like this. I'll write it this way first. Cube root of x, the sixth root of x, minus 2 equals 0. All right. Well, certainly would help to write this as x to the 1/3 plus x to the 1/6 minus 2 equals 0. Again, you'll notice these exponents have a common factor. So that suggests making y equals x to the 1/6. Well, let's see if that's going to help us. This becomes y squared. This becomes y minus 2 equals 0. Okay, so once again, we modify this so it's a quadratic, something we're more familiar with solving. Again, let's apply quadratic formula here. Negative b plus or minus square root of b minus 4. It's nice we have a minus here. This would be minus plus minus 4ac all over 2. Negative 1 plus or minus plus 9 is 3 over 2. And we're going to end up with 1. Minus 2. This of course is y. That's not our solution, right? We have to say x to the 1/6 equals 1. So therefore x equals 1. And x to the 1/6 equals minus 2. Well, let's raise this to the 6th power. That's going to be x equals 2 to the 6th power. Again, computer science people, know your 2's. 2, 4, 8, 64. Now, again, as in with radical equations with radicals, these are equations with radicals, we want to be a little careful because we can get phantom roots. So let's first try the 1. Well, the cube root of 1 is 1. The 6th root of 1 is 1 minus 2 equals 0. So that works. That's the root. All right. Let's look at 64. Cube root of 64. And this is if you're good with the 2's, you know that's going to be 4. The 6th root, well, we already know that's 2. That's 6. Not equal to, plus 2 minus 2 equals 0. 4 equals 0, that's not true. So this is a phantom root. Again, you can get those, you don't always, you can get those when you're dealing with radicals. roam away. All right, the last type of equation we're going to look at today is an equation with an absolute value. Now this would be fine, this would be a nice linear equation without the absolute value sign. We know how to solve it that way, no problem. But putting those in adds a constraint. You see, we know that whatever's inside the absolute value sign, it's going to end up either being positive or zero. So, for example, if 2x minus 5 is greater than 0, greater than 0, we have this equation, 2x minus 5 equals 3. We can just take it right out of the absolute value sign. However, 2x minus 5 is less than 0. That transforms the equation. That means we have to take whatever's in here and multiply it by minus 1. Well, in this case, we can just do this by switching these around. So now we've taken our absolute value equation and we transformed it into two linear equations we can solve. And these are fairly easy. This is 2x equals 8 or x equals 4. And this is negative 2x equals minus 2. Minus 5 is minus 2, or x equals 1. Now, as with equations with radicals, equations with absolute values can produce phantom roots. That is, we've got two roots here, but they may not work, and we have to check. So let's try that. Plug in 4 first. 8 minus 5 is 3. 3 equals 3. All right. Good. Let's plug in 1. 2 minus 5 is minus 3. It's 3. Okay. So in this case, they're both good. You want to check. I don't know why. I'm just. It's for problem solving, so. Often more than one way to come upon an answer. One thing we might do is we might want to graph this. I think we do graphing later in class. We take two equations. You might want to see where they intersect. That should give us the solutions too. Look like 1, 2, 3, 4. Now, if you've graphed an absolute value before, you know it's kind of going to look like this, or like this. And this point here is going to be the point where this is 0. So that's going to be, where's 2x minus 5 equal to 0? Where x equals 5 halves. So that's 2.5. And the slope, this is, on either side, we're going to have a slope of 2. Like this. Or we're going to have a slope of -2. Sure enough, if we graph the other equation, y equals 3, you end up with these 2 points instead of both. It didn't really come out very well. 4, yes, was here. My graph isn't very accurate. You know, get some graph paper or use Desmos. All right. The last thing I'm going to say about solving equations, I know students love to hear this, it will not be on the exam. Certainly. I just think it's just a little trivia that it's useful to know when you're going off into life and you're dealing with mathematics. Of course, if I have the equation ax squared plus bx plus c equals 0, we all know now that x can be negative b plus or minus the square root of b squared minus 4ac a. I think I might have mentioned that, this was known, it was known how to solve some of these equations by the Greeks. They didn't have algebra, they had geometry at their, to use. Depending upon which history book you look at, either the Middle East came up with algebra, or maybe in China, maybe in Asia. That was back, we're talking a couple thousand years ago. But if you look at the next step, a cubic equation, nobody knew how to solve that in general for a long time. It was solved in, well, I'm just going to say the 1500s by an Italian by the name of Niccolo Tartaglia. Actually, I think Tartaglia may just have been kind of a made-up name they gave him. And just so you know why you never want to use this, you could. The computer science people set up a computer program to do this. This is what the solutions look like. This is your set of your quadratic formula. Look it up on the web or in my notes. Not done yet. No, I left that too. I'm not done. Well, all right. This just looks a lot like this. Take my word for it. And finally, we have to subtract b over 3a. Oh, these are cubed roots. Doesn't it sound like fun? Here's the worst part. Often when you're using this formula, this square root, this one? No, not this one. You'll often end up with an imaginary number that just happens to drop out when you add everything up. Yes?
How does this pertain to computer science?
Well, let's say I'm your computer science professor, and I say, I want you to write a program that's going to solve polynomial equations. And insofar as it's possible, I want you to solve them exactly. And if not, solve them numerically. Right? So, if it's a linear, well, that's trivial. If it's quadratic, we get a quadratic equation. It's just a formula. If it's a cubic, you can plug this formula into the computer. Come up and say, this is, you might have to do some careful formatting. You might end up with a square root that you can't reduce. There's also an even more complicated formula for the fourth degree called the quintic. It was discovered shortly after this came to its discovery. So, it would be a nice project, then you might want to try and apply, see even if it's a fifth degree or greater, you might see, is this just a simple enough that you can solve it using factoring. There's actually I'm not going to go into it, it's a math major kind of formula, but you can come up with it as a CS major to explain how you know when you can factor something like, a fifth or a sixth degree. There's no general formula, so you might have to use a numerical. But you can see where just plugging in this formula is at one level it's kind of trivial, right? Add this, multiply this, and so forth. But that would be kind of a neat program to write. Is that an okay answer? All right. And as I mentioned, I think they may have mentioned, it took another 200 years to figure out why we couldn't find a general formula for a fifth degree. Again, if you're a math major, you'll someday discover what that's all about. This was determined in 1820 by Niels Adel, famous mathematician. Yeah. So again, I just thought, have a big context for what we're doing. Solving equations is a big deal in math. And we ran up into a problem trying to solve anything that's greater than fifth degree polynomial. All right. I think I'm going to just talk for a couple minutes about the next phase of this. It is solving equations. Up till now, we've only been interested in equations whose solutions are real numbers. But as some of you may have come across previously, this equation is kind of problematic. You try and solve it. Say, all right, x squared equals -1, or x equals plus or minus the square root of -1, which certainly to anyone up to 7th or 8th grade, you're told, well, no, right? How can you multiply two numbers and get a negative number? Right? Take a real number, you multiply a positive by a positive, you get a positive. A negative by a negative, you get a positive. So it seems impossible. But it turns out that there are things, there are real-world situations, there are electronic, formula for what you might use in an E&M class. There are formulas you might run into in physics, where there's something that actually operates the way these numbers, call them imaginary, function. And we can develop mathematics to use them that's quite consistent, except for that difficulty of getting over how do you even get such a number. They make sense. So, as I said, we call these are imaginary numbers. And we extend our idea of what a number is into something we call a complex number, which has the form a plus bi, where a and b members of the real numbers. I is defined as the square root of -1. And we call these complex numbers. We also, just like we show a real number on a number line, we'll describe the complex numbers as a point on a plane where in the x direction we have the real component, in the y direction we'll have the imaginary component. So this will be from AB, where the number is a plus bi. Now, complex numbers are, in some ways, a little different from real numbers. We're going to be able to multiply them, add them, subtract them, divide them, do all sorts of things, find their square roots. However, there's one notable thing that's really different. For any two real numbers, one of three things is true. A is greater than B, B is greater than A, or is equal to B. That's not true for complex numbers. They don't have a natural order. You could try and create an order. You could say, well, how far is this number from the origin? You could assign them a number and then a real number and then order them that way. But they don't have a natural ordering. All right, that's actually, I just wanted to give you a little introduction. We're going to talk about working with complex numbers on Tuesday. And that's all, folks.